These dog treats may just look like another homemade snack, but there's actually some real chemistry baked into them. Today, I'll walk you through how I made these peanut butter, egg, and flour cookies for my dogs and break down the science happening at every single step. From how the ingredients interact to what changes when we apply heat, this is chemistry in the real world. Delicious, practical, and pet approved. To make these simple treats, I only used 4 ingredients: 1 egg, half a cup of peanut butter, and 1 cup of flour. Let's start with the egg. Eggs are full of protein like albumin. When you whisk an egg, you're physically unfolding these proteins, and this process is called denaturation. It's not a chemical change just yet, but it's an important first step. Denaturated proteins have more exposed bonding sites, which make them better binding agents. They help the treat hold its shape and structure, especially during baking. Later, when we apply heat, these proteins will coagulate, and that's a true chemical change where new permanent bonds form, turning the liquid egg into a firm, solid structure. Next up is peanut butter. This part takes some patience. Scooping it neatly into a measured cup isn't easy, but measuring accurately is important because peanut butter adds fat, protein, and a little moisture. It also affects how soft or firm the cookie turns out. From a chemistry standpoint, peanut butter is mostly non-polar fats. These molecules don't dissolve easily in water, and that'll matter a lot when we try to mix it with the egg. Also, super important for dogs, make sure you're using peanut butter without xylitol, which is toxic to pets. Check the label. You'll want natural, simple ingredients. Fewer additives means fewer unpredictable reactions. Xylitol is a sugar substitute, and it's super toxic to dogs because it triggers a rapid and excessive release of insulin from their pancreas. This leads to a dangerous drop in blood sugar levels, also known as hypoglycemia, and can also cause liver damage in some cases. So, as I mix the egg and the peanut butter, you'll notice that they start to resist combining. This is because they're chemically incompatible. At first, polar and non-polar substances don't naturally blend together. What you're seeing is the beginning of emulsion. With enough mixing, the mechanical energy that you released from mixing it with your arm breaks the fat into smaller droplets, which in turn suspends them in this water-based mixture, which is the egg. It takes a bit of effort, but eventually you get this thick and sticky texture, the perfect dough consistency, if you will. The consistency here is due to the increased viscosity, which happens when fat and proteins start interacting in a semi-stable structure. It's a physical change at this state, but nothing permanent yet. So as you can see here, I'm going to start adding some water, only about 1/4 cup. This step helps reduce the overall viscosity or the thickness of the dough, so it'll be way easier to mix. Water is a polar solvent, meaning it's really good at dissolving other polar substances, as well as helping them spread out evenly in the long run. Once added, it starts interacting with the egg proteins, and it also helps hydrate the flour that's going to be coming up in our next step. It also helps cool down those fat molecules from the peanut butter a little, which makes them easier to disperse. You'll notice that when I start mixing it all together, the texture kind of starts to shift. It's less thick and more uniform. Although this is a super small step, it plays a huge role in the dough's final consistency. We're still in the zone of physical changes, and no new molecules are forming, but everything is getting more integrated and more balanced. It's flour time, one of our most critical ingredients for the structure and the texture of the treat. I'm using 3/4 of a cup, as you can see here. The line for 3/4 starts at the inside of the cup, so I'm going to be filling it to that line. If you have a 3/4 cup, you can use that as well. And I'm making sure to measure it as accurately as possible. I'm going to gently scoop the flour into the measuring cup without packing it down. Then I'm going to level it off with a flat edge to get an even amount. Not too much, not too little. Measuring flour precisely might not seem like a big deal at first, but it actually has a huge impact on the final product. If you add too much flour, even though it's just a couple tablespoons, the dough can turn out stiff, dry, or even crumbly. On the other hand, not adding enough dough can leave it sticky, loose, or even too wet to shape. That's because flour is more than just a filler. Chemically, it's made of long chains of carbohydrates, proteins, and starch. When these molecules come into contact with water, they begin to absorb it. This triggers gelatinization, a physical change where starch granules swell and trap water inside of it. As I stir the flour into the wet mixture, you'll notice that the texture starts transforming from loose and runny to more uniform and compact. That's the starch and gluten creating a network, a soft protein starch matrix, if you will. It gives the treat its structure and form. The dough becomes less shiny in return, more matte, more pliable, and it's thick enough to mold, but not too dry or too crumbly. It's important to not overmix either. Too much stirring at this stage can overdevelop the gluten, making the cookies too dense or tough after baking. Right now, everything we see here is still a physical change. Nothing new is being chemically formed just yet, but we're preparing the dough so that when we apply heat later, it can go through the chemical changes that we see and that will set everything into place. This balance of water, fat, and flour is what makes the perfect dough. Pliable, structured, and bake ready. Now I'm going to get the dough ready for baking. I'm going to be using parchment paper for a few reasons. It's coated with a silicone, so it's a non-stick and it's also heat resistance. That means the cookies won't burn on the bottom, but it also creates a tiny buffer zone between the metal tray and the dough. Plus, it makes cleanup super easy, and who doesn't love that? So here, I'm shaping the dough into small rounds, and I'm placing them on the tray. The dough is still thick and pliable, and these are all thanks to all the physical changes we made earlier with the flour and the eggs and the peanut butter as well. So now I'm going to be shaping these into teeny tiny circles. Now that I've finished shaping all the dough into small rounds and placing them on the tray, I'm going to create that classic peanut butter cookie crosshatch pattern. This isn't just for looks. It actually increases the surface area, which helps the cookie bake more evenly and dry out uniformly in the oven. So I'm going to be doing this with all the cookies. You might have trouble if the dough sticks onto the fork, so I'd recommend putting some cooking oil on the fork beforehand. And yeah, you should have this. Into the oven they go. I'm going to be carefully placing the cookies in the oven, and I'm going to be setting it at 350 degrees for 30 minutes. And here is where the real chemistry happens. So inside the oven, the egg proteins fully coagulate, which form irreversible bonds, and the starch in the flour complete that gelatinization process we were talking about earlier, and they begin to firm up. And the water inside the dough, it begins to evaporate, which lowers that moisture content. The evaporation leads to a mass loss. So if we were to even weigh the cookies before and after baking, we can calculate how much water that was left in the dough. These changes are both physical. It's like turning water to vapor, and chemical as well, like proteins forming new and permanent structures. This is the transformation from raw to cooked. And there you have it, homemade dog treats powered by chemistry. We explored physical changes like mixing, emulsifying, and gelatinizing, and chemical changes like coagulation, evaporation, and mass loss. We saw how heat transforms food and how molecules interact. And so next time you're baking, even if it is just for your dog, remember, you're not just cooking, you're doing science. Thanks for watching, and I hope you enjoy those tail wags. Bye!